Well, good afternoon, everyone. It's my pleasure to welcome you all to the 15th Annual Husson University Research and Scholarship Day and the plenary session that will feature Dr. Cardon as our speaker. But first, there's a couple of other announcements that I'd like to make, and particularly the first one is to thank members of the committee that helps put this together. Specifically, Dr. Robert Brooks, Cody Edson, and Evan Wigton-Jones. And I'm also the chair of that, and my name is Dr. William Lindblad. So this event that we've had today, and hopefully you've had an opportunity to take a look at the posters and maybe listen to the oral presentations this morning, is our annual celebration to research and scholarship of all sorts at the university. And we're very pleased to have all the students that participate in it and really gain from it in terms of a learning experience. And so one of the things that goes along with that is we do an evaluation of the posters. We have two independent evaluators that review each poster and rank it in terms of creativity and content. And at this time, I have the results. It's not in an envelope on my front porch, but in any case, this year was one of the most competitive in terms of the final results. And for the first place winner, they receive a $100 Amazon gift card. The second highest ranked receives a $75 Amazon gift card. And the number one poster for today is the one that was listed as physical therapy number 5, which was the impact of a physical therapy education program on implicit bias and cultural competency. So maybe a round of applause for. So they will receive $100 gift card, and also we will have that poster mounted outside of the provost's office for the next, basically until the end of the academic year. And the other poster that was very nip and tuck was the one from Pharmaceutical Sciences, deletion of divalent metal transporter homologs in C. elegans prevents lanthanum and ytterbium-induced oxidative injury. And a round of applause for that one, too. And so at this time, I'd like to welcome the provost, Dr. Victor Brown, to the stage to present an award for faculty research.
Good afternoon. Good afternoon. Let's try this again. Good afternoon. Good afternoon. Thank you. My name is Victor Brown, and I serve as Husson University's Vice President for Academic Affairs and Provost. On behalf of Husson's President, Dr. Lynn Yogan, along with our faculty, staff, and students, it's a pleasure to welcome you to Husson University's 15th Annual Research and Scholarship Day. Today's event spotlights over 30 oral, poster, and video presentations. It provides a platform for students and faculty to share innovative research with the broader university community. Today, we come together to celebrate research and scholarship, not only for the vital role it plays within our university, faculty, and students, but also for its broader impact on our local, state, and national communities. The presentation at today's event have advanced our collective knowledge and deepened our sense of purpose as an institution. They reflected the curiosity, dedication, and innovation that define Husson University. Before Dr. Lindblad introduces today's keynote speaker, it is my privilege to present the 2025 Distinguished Faculty Research Award recipient. This prestigious award is given to a faculty member who has demonstrated exceptional scholarship achievement as recognized by his or her peers. The recipient was selected through a competitive review process and will receive a $1,000 cash award along with an engraved medallion to be worn at commencement in recognition of his or her outstanding contribution to research and scholarship. The 2025 Husson University Distinguished Faculty Research Award is presented to Dr. Dajong John. Let's give her a round of applause. Dr. John was selected for her impactful and diverse research in health and labor economics. Her work includes examining the spillover effects of Medicaid expansion on elderly Medicaid beneficiaries, as well as analyzing the broader implication of Medicaid expansion for adults under 65. Specifically, its influence on health outcomes and access to insurance coverage. Before joining Husson University, Dr. John served as a research fellow at the University of Melbourne in Australia. Her scholarship has been published in a range of respected journals, including Economics Letters, BMJ Open, Australia Journal of Social Issues, Social Science and Medicine, and Health Economics. Among her many noteworthy contributions, she has presented on social relevant topics such as the effects of the dependent coverage mandate on working fathers, job mobility, and compensation. Dr. John's dedication to applying empirical methods to real-world challenges enriches the Husson University community and exemplifies the spirit of this award. Her pursuit of knowledge continues to inspire students and colleagues alike. Please join me in congratulating Dr. John once again on a well-deserved honor. Before Dr. Jung shares her research with us, I would like to take a moment to recognize Dr. Bill Lindblad, Professor of Pharmacology and Director of the Office of Research and Scholarship, and express our deepest appreciation for his outstanding leadership. Please join me in giving him a robust hand of thanks. After 17 years of dedicated service to Husson University, Dr. Lindblad will soon begin a well-earned retirement. His contributions have left a lasting legacy, and we're committed to honoring that legacy by continuing to be excellent stewards of Research and Scholarship Day for years to come. As we look to the future, we're excited to build upon the strong foundation Dr. Lindblad has established. The Office of Research and Scholarship will continue to grow and evolve, supporting a culture of inquiry, innovation, and academic excellence across the entire institution. I would like to also extend heartfelt thanks to this year's planning committee members. They are Dr. Robert Brooks, Dr. Cody Edson, and Dr. Evan Wigton-Jones for their time, effort, and commitment to making the 15th Annual Research and Scholarship Day a success. Thank you all for your great work and dedication. Please give them a hand of thanks. Thank you for joining us in recognizing and celebrating the incredible work of our students and faculty. We look forward to the continued growth of research and scholarship at Husson University in years to come. At this time, I invite Dr. Jung to come forward and receive her medallion and her award and to present her findings to you. Dr. Jung.
Hello, my name is Dajong Jun, and I'm assistant professor at the College of Business. First and foremost, thank you so much for this recognition. It is truly an honor for me to receive this award. As an economist, my work lies in the field of the applied microeconomics, especially with the focus on health and labor economics. More specifically, my work has focuses on how the public policies, especially in healthcare, could affect the individual's lives from access and affordability to the long-term, to their long-term care and to their long-term well-being. And I'm very grateful, by the way, I'm very grateful to my collaborators, mentors, and students whose inspirations and support continue to shape my research. And this recognition motivates me to further develop and focus my research on research that actually informs the economic policy. And here I would like to take a moment to briefly introduce my work and the focus of my research. So, broadly speaking, my work has been focusing on how health policies influence the individual and population-level outcomes, with an emphasis on health inequalities, access to care, and economic and behavioral effects of public programs across the life course. So the first strand of my research focuses on mothers and their infants, which is more about the intergenerational effects. So the one set of my work focuses on the health insurance tax credits, the impact of the health insurance tax credit, which is designed to work alongside with the earned income tax credits for low-income population. So this work shows that the health insurance tax credit, this provides incentives for low-income mothers to obtain health incomes, attend more doctors, to obtain health insurance, attend more doctor visits, and increase their overall healthcare utilization. Another strand of this research focuses on opioid crisis, which is often discussed in terms of the mortality statistics. But in our case, we actually examine its opioid crisis overlooked effects on survivors, particularly on maternal and birth outcomes. And our work actually shows that the states without the prescription monitoring programs, they experienced a significantly higher rates of the low birth weight following the introduction of the OxyContin, which was introduced in 1996. And this work highlights that the opioid crisis harmful consequences for the newborn health and underscore the need for the stronger prescription drug regulations. And the second set of my research shifts the focus on the Medicare population. So again, this Medicare population is another vulnerable group that relies heavily on the healthcare services, often while managing the limited financial resources. So one of my recent research, which was published at JPAM, examines the spillover effects of the Medicaid expansions, which is through the ACA, on Medicare beneficiaries. So by using the Medicare administrative data, we examine whether the Medicaid expansion of the ACA influenced the Medicare spending among the low-income populations. And what we actually find out is that Medicare spending, due to this Medicaid expansion, Medicare spending decreases, and the dual coverage with the Medicaid increased with no measurable adverse effects on mortality. So our findings highlights here is that the low-income individuals, once they are eligible for the Medicaid, they were able to address previously unmet health care needs that they might have otherwise postponed until enrolling in Medicare. So they can actually get the care without delaying it until they enroll in Medicare. The last line of research that I would like to highlight is about the naloxone access. So since the early 2000s, the opioid overdose death has been more than doubled. And this naloxone, which is a life-saving opioid antagonist, has become increasingly available through the naloxone access laws, while the empirical evidences on this law has been limited. So our work is actually the first work that examines how the naloxone access laws affect the opioid-related hospitalizations or the ED visits among the Medicare beneficiaries. So and our finding shows that the naloxone access laws reduce the opioid overdose fatalities and thereby lower the use of the acute care services without the potential concerns about the moral hazard. So this is the brief overview of my current research. And if you have any questions or concerns or even like feedback, please feel free to reach out to me anytime. And again, I truly appreciate this award, and I will view this moment as a new opportunity to further develop my research. And I'm also looking forward to supporting the students and faculty who have a shared interest and further contributing to broader research initiatives at Husson University. Thank you so much.
So now it's my extreme honor to introduce the plenary speaker this afternoon, Dr. Cardon. And just for a brief background on Dr. Cardon, who is currently the president and CEO of the Jackson Laboratory down in Bar Harbor. Dr. Cardon joined the Jackson Laboratory in 2021 after serving as Chief Scientific Officer and Chief Scientific Strategy Officer at BioMarin Pharmaceutical Incorporated, a California-based rare disease biotechnology company. Prior to BioMarin Pharmaceutical, he was Senior Vice President and Head of Genetics, Quantitative Sciences, and Alternative Discovery Development at GlaxoSmithKline for 9 years. Dr. Cardon's academic career began at the Institute for Behavioral Genetics at the University of Colorado, Boulder, where he received his doctoral degree with postdoctoral training at Stanford University in the Department of Mathematics. He subsequently became a faculty member at the University of Oxford in England, initially as head of bioinformatics and statistical genetics at the Wellcome Trust Center for Human Genetics, and later as a Wellcome Trust Principal Fellow and Professor of Bioinformatics. He then moved to the University of Washington as a Professor of Biostatistics and co-chair of the Herbold Bioinformatics Program at the Fred Hutchinson Cancer Research Center in Seattle. Dr. Cardon has published extensively in the fields of genetic methodologies, applications, and discoveries in rare and common diseases, resulting in over 225 scientific publications and 15 books and chapters. His research groups have discovered dozens of genes for common and rare diseases, and his involvement as co-founder of the Wellcome Trust Case Control Consortium led to the first genome-wide association study. His contributions to the genomics fields have been recognized by election to Fellow of the United Kingdom's Academy of Medical Sciences and the American Association for the Advancement of Science. And today, the title of his presentation is Genomics, Drug Discovery, and AI, Fulfilling the Promise or Chasing the Hype. Dr. Cardon.
Well, it's a real pleasure to be here today, and thank you so much for the opportunity. My first time on campus. You have a really beautiful campus, and congratulations for that. I like to tell stories. And so with a diverse audience like this, what I thought I would do is put together a few different vignettes of different activities that have been going on in the world that I live in for a while, and hopefully there'll be some things that resonate with some of you along the way. We'll talk a little bit about the Jackson Lab, because we're just 60 miles away, and it's a very exciting place. It's been around for nearly 100 years. The student program celebrated its 100th year last year. I want to talk a little bit about some advances in genetics. I'll apologize now. I'm a geneticist, and I see the world through DNA. Everything works that way, and so all my stories will come out that way. I want to talk a little bit about the future and where things are going and the challenges and the opportunities in the field. Before we do, go there, if I can operate this device. So I thought I would just do a little introduction to myself because it's relevant. I like to use some version of this speaking to students. I will break the cardinal rule of mentorship right now and say I never had a path. So when you get gray hair and you get older and people say, what was your dream? What was your, apart from breaking devices, what was your plan all along? I didn't have one. right? And I have been accused of being a dilettante along the way because I started out as an academic, then I went into industry, and I came back to academia, went back to industry, came back here. And so that's a pretty strange path. And in my day, nobody did that. Now it's a little bit more common, but not then. But what I had was a belief in the future of my discipline. I fell in love with genetics and the ability to think if you can reduce the understanding of disease down to its most fundamental core, then you can do something good in this world. And the rest of that was just taking paths trying to follow that dream. I didn't have a desire to go to industry and back to academia. I wanted to pursue genetics and see if we could find the genes that cause disease and do something about it. And so that was the path there. And so those of you that are a little uncertain of your future, there's hope for you along the way. And I was glad that we had the slide in because just seeing your posters there's so much to resonate. As an undergrad, I went to a small liberal arts school, almost the size of you, maybe just a little bit smaller. And I was reflecting watching the posters in my junior year. A very, very kind professor of psychology actually took me under his wing and introduced me to what real research looked like. And it was really fortunate. We actually published the paper together in my senior year. But that project right there set the course for my entire career. I fell in love with research. I thought it was fun to go through the peer review process. I thought the research itself was fun. I thought discovering things and then realizing they're wrong was exciting. So what you're doing right there is just wonderful to see. So enough about me. A little bit about the Jackson Lab. So as I said, it's nearly 100 years old. It's quite a big institution now. We've got 12 sites globally, 4 of which are in Maine, 3,000 employees, a lot of PhDs, a lot of Nobel Prize associations, and some that came straight out of the lab. My first year there, 3 years ago, I was just mentioning, we teach this beautiful course. You should come over in the summertime called the short course on genetics. It's been being taught for 67, 68 years at the Jackson Lab, and the good and the great of human genetics and animal genetics throughout the world pass through Bar Harbor each summer. They're there for a couple weeks, and they're teaching, and they're interacting, and doing what they do. My first year, the last speaker, sort of the plenary speaker of that conference, gave his talk. It was terrific, and 2 weeks later picked up the phone to hear that he had just won the Nobel Prize. So that's the type of people we get through. It's really quite impressive, but it didn't start that way. I might have broken this device. So this was our first Nobel Prize winner, George Snell, and he really was one of the fathers of current immunology. So if any of you have relatives on immunotherapies right now, on cancer drugs, you kind of thank this guy for it originally. Personally, I really like this slide because at the back of that, if you see behind him all those the little checker things, the field he created, called the Major Histocompatibility Complex, or HLA in humans, has the most convoluted nomenclature that you could ever imagine. I suspect he may have won the Nobel Prize because he was the only one who could understand it. It was really, really complicated, but it was a huge development. And there's a theme that I want to put through today, that very bottom bullet point. When we find genes for disease, the genes, or for anything actually, the genes tend to get named based on what disease or clinical symptom that they were first found with. And you see this in fruit flies are the greatest to see it. So if you go through, they have very colorful names of genes in fruit flies. So wingless would be a fruit fly gene name because those flies don't have wings, right? We do the same thing in humans. So his first understanding of the immune response came from a gene that was first identified for a fused tail in mice. And the message there is we have about 20,000 genes in humans, about the same as those fruit flies, not far off, but they do lots of different things. And that's partly what the field is now discovering as we turn genetic discoveries into drug discoveries. And that's something I want to come forward through. But the very first person was this fellow. C.C. Little was his name. And he was a physician and really invented the use of laboratory mice for the study of human biology. And he invented it because what he realized is that some mice will get tumors, disfiguring tumors, that looked kind of like what humans get. And he thought, well, I can't really investigate humans in an experimental way, but maybe I can work on these mice. And he started it, he was professor of medicine in Michigan. But mice don't do as well in Michigan as they do in Maine, actually, in terms of survival and the temperate climate and that sort of thing. So he brought that, that's how it ended up in Bar Harbor. He brought this out to Bar Harbor and started this, this operation. And that mouse he's got there, the way genetics works in mice is quite fascinating, really, is they inbreed mice, brother-sister matings, again and again and again and again. So the mice, after some number of generations, are absolutely identical to one another. So if you go into the catalog, as you could, go up after this meeting and say, I want 100 mice of this particular strain at the Jackson Lab. You can get 100 mice, and they're clones of each other. They're all exactly the same genetically, right? Then you can get a different species and say, okay, I want 100 of these type, and they're exactly the same of each other, but not the first ones. So you can use that, and that's how the genetics work, because you've homogenized the entire genetic background. He sort of discovered that and pioneered it. But he also was kind of unlucky because right about the time they were getting this off the ground as a research entity, the stock market crashed in 1929. And so what he realized was that the study of mice not only is useful for biomedicine and for research, but others might like it too. So he started selling the mice. And that's why you take an organization from a couple of people, a couple of students looking at mice into something that's got 12 sites around the world and 3,000 people or something. So we provide the laboratory mice for virtually every hospital, every research institution on the planet, one way or another. So that's what it looks like now. 2,400 organizations, 68 countries, 14,000 different strains of those different types of inbred mice. 80% of all mouse-related research cite a JAK strain industry standard. So out of someone who just was following his dream. He was interested in the mouse. I love this. I was down in Washington for not very great reasons lately, which is common. But someone handed me this mug and said, because mice have been used in virtually every drug ever approved by the FDA since they've been since they required animal usage, I don't know if this is true. This would need to be fact-checked, where they really saved more than 911, but they have saved a lot. What I do think, I believe to be true, is that every drug approved by the FDA has either been through a mouse originally designed at the Jackson Lab or currently designed at every single drug that we use today. So there's a good footprint there, and it's something that we're really, really proud of, and I have the great privilege of leading this organization to do that. But it's not just a mouse sales facility. That's not, we do a lot of that, and we do a lot of partnering with others, with all these research institutions. We kind of have a two-pronged approach. We have that mouse organization, most of which is in Maine, but not all. We have California, we have Japan, we have a holding pen in Heathrow in London, and but we also have a nonprofit research institute, just like Memorial Sloan Kettering or the Fred Hutchinson Cancer Center or something, and we do our own research. And these are the research, we have a lot of research areas. Two I want to talk about today are rare diseases and cancer for genetics reasons. So what we really do is we have our research side, this is kind of our mantra, that discovers solutions, our own research, and we have the mouse provision side that empowers others to do it for the community. And that's who the Jackson Lab is. And as a shameless plug for interns, projects, collaborations, we're only 60 miles away for all these things. So that's a little bit on the Jackson Lab, and I'll come back to some other projects going on, but that's the background. I want to talk a little bit about genomics and my perspective on the history and the promise in this field. So I made this slide a long, long time ago. And I don't know how many of you know of the hype cycle. I'll explain what it is in a second, but you're forgiven if you don't. Because when I first made this slide, I was absolutely convinced I invented this. And I'll tell you why I thought I had invented it from the field of genetics I was in, but I had this very introverted postdoc come up and say, Professor, you didn't. That hype cycle has existed for a long time. So what this is, it happens a lot in tech. You get a new iPhone or something, or different new inventions. It's called the Gartner hype cycle, and something new comes along, and it's super exciting, and everybody latches onto it and thinks it's going to be the next thing that put man on the moon. And then it kind of doesn't really deliver in the time frame that they hoped for, so everybody kind of turns their back and runs away, and about the time everybody's gone and not interested anymore, it actually starts delivering on that promise. That's the hype cycle. And in medicine, that is absolutely the case. Just you can say gene therapies, monoclonal antibodies, pick your example. It went through something like this, and it's usually somewhere around 20 years. So I was a young geneticist in the early 1990s, and that was the time when the field was starting the Human Genome Sequencing Project. Right? This was a $3 billion project to sequence, really it was a mishmash of people, but one person. So that was the Human Genome Project. That's pretty expensive. Those same genomes right now are less than $1,000. But back then, it was just getting off the ground. It was so exciting because the dream was if only we knew we could find the genes that cause disease, that drug discovery thing is easy, right? So if we know the cause, then we can do anything. The field of genetics at that time was, I love to say this, and it happens to be absolutely true, genetics wasn't a big popular discipline like it is today. It was very, very small. And to give you an example, the conferences, scientific conferences that some of you will go after your posters, that we went to would be in the lowest caliber meeting room in a Marriott, in the basement, where we would sit and there'd be maybe 50 of us, maybe 100 of us, and we'd sit and debate whether there even exist genes that cause disease. Now, if you go to the back end of this thing, now that those same meetings, 2 years ago, there were 10,000 people there, and it was opened by Maroon 5. And back then, it was Coke bottles and all that. So the field has come a long way. We went from knowing 1, 2, up to maybe 10 genes that cause disease. There was an early breast cancer gene. There was an Alzheimer's gene, a couple. To now there are, in terms of positions on chromosomes that are associated with disease, more than 100,000. We know genes associated with everything. You name it, people have studied it out there, and there are genes that are associated with it. But what happened was, as the Human Genome Sequence Project went on, it fulfilled its promise, and we had one consensus sequence of DNA, but nothing came out the back end. Where are these drugs? Where is this transformation? What happened? Nothing, and so that's when it crashed down. That's the hype cycle. That's where I thought I invented it. And it has come back up for some. So the reality of this field, and I can say this because I'm in it, and it'll be contentious and others will argue, it has been wildly successful in some areas. It's been wildly successful in finding genes just about in every area, but in terms of translating those discoveries into something that improves our human health in one way or another, only a few areas. Mostly we haven't got there yet. I'm holding these batteries in because I've thrown this. So the puzzle pieces that we need, it's a frustrating time, actually. It's a wonderful time, but it's a frustrating time, too, because it feels like we have everything we need. Imagine you're doing a jigsaw puzzle. You've got all the pieces are right in front of you. You've got all the tools that we need to solve this problem and translate genetic discoveries to disease. But they're upside down. You just don't know exactly how to put them together to get there. That's how I feel the field is right now, except in really two areas. And the first is cancer. If you take cancer therapies today, so you just look at this graph and look at the y-axis, those are approvals of drugs in cancer over the last, you can see the x-axis on the number of years. And a lot of those, all the red there, are targeted therapies, which means one way or another they probably had a genetic finding that led to those. It's massive, huge success in cancer. And if you think about it, if you think back, those of us that are old enough to think back, 50 years ago or so, Richard Nixon, who was the president at the time, declared the war on cancer. And at that time, you can pick your cancer, I'll choose breast or lung cancer, it'd be the same. We thought of cancers like that based on the tissue or the organ that they attacked. Breast cancer, one disease, that was it. Ovarian cancer, one disease. Today there are 80 different subtypes of breast cancer, each of which has its own treatment. So, or prostate cancer. My prostate cancer, if I have, is not the same as someone else's, and the treatments aren't going to work the same as someone else's. we thank genetics in large part for that, and that's what has happened with cancers. So this is a great success story coming out of the Human Genome Project and all that time. So I'll skip that one. I want to tell you this project. So you think of all that cancer, clinical trials. I'll talk about drug discovery in just a little bit in a minute, but clinical trials are the process by which you make a drug and you start testing it in humans. You don't know if it's going to work yet, but you're testing it in different humans. Right now, at any given moment, ask yourself in your head, in smaller audiences, I go around the room to have guesses. How many clinical trials are ongoing today in the world for cancer? And just ask yourself, think of it. The answers people mostly get to me when I see this, sometimes they'll be 200. Sometimes somebody will say 3,000. And the answer is more than 20,000 clinical trials ongoing for cancer today. So ask yourself this. You have the unfortunate position of being diagnosed with cancer. You go to your doctor, and they're going to give you a genetic test, and they're going to try to find out which one of those subtypes of cancer you've got. How likely is it that any physician can know 20,000 clinical trials at any given time? No way. Right? They're going to be lucky. They're busy. They're going to be lucky if they know the regimens that have been approved and that are in front of them and that they can go through. What if your type of cancer isn't on the list that they're familiar with? And the likelihood is it's not, because there's 20,000 clinical trials that aren't those. So this was a recognition. I just love to tell you this story. Jackson Lab led it, but it's science by crowdsourcing. So there was a recognition. I think you could only start this in Maine, actually. Maybe other rural states, but Maine is particularly good. They recognize that none of the physicians in Maine or anywhere are going to know everything about cancer that they need to know. But collectively, they could share resources, and you could bring in genomics tools and expertise to try and find the right location for your cancer. So you come in, you get your clinical test, and they have these genomic tumor boards. They have this collection of super intelligent people from across the globe that come and look at your particular type of cancer and say, oh, there's a drug trial going on in Iowa for that particular, and that's where you need to go. And so they put that together. Every practicing physician in this state, oncologist, participates in this right now. They've been doing it since 2016. And the beauty of this is this is not a well-controlled clinical trial. This is a study in the wild. You take what you get, right? These are just cancer docs bringing their patients material. They can act on the findings or not if they say they want to send you to that clinical trial. 31% higher chance. It saves lives to just have the physicians talk to each other. Now, the reason I say that has to start in Maine is because if we went to, I usually pick on Boston, but I'll take my hometown of Seattle on this. We went to Seattle and we tried to do this. The physicians are competing for patients and they're competing for resources. No way are they likely to collaborate like this, when in fact that might be the very best thing for the patients themselves. So I'm super proud of this. And the challenge now is, can we get it all the way across the United States? And that's what we're trying to do, and we've got studies to do that. It's a funding problem, but a really, really exciting one. So that's a vignette for cancer that you should take advantage of it, because anyone, family members, anyone in Maine, and I don't even think they distinguish that you have to live here, but you can participate in this study. And I don't see why we don't do this for other diseases. It's super, super powerful, and it didn't take a really rock star cast of new discoveries to bring it to life. It took communication. So let's talk about rare diseases. Okay, so rare diseases, this is kind of the equivalent type of FDA approval slide as I showed with the red with cancer. Rare diseases also have had terrific success in recent success in drug discovery. So what are rare diseases? So rare diseases are those things that people often don't talk about, but almost everyone is familiar with, because collectively there's something like 10,000 rare diseases. And by a rare disease, it just means it's infrequent. And there's a definition in the US, it's like 1 in 200,000 births or something makes it a rare disease. So it's not type 2 diabetes, or it's not hypertension. It's something less common than that. These are diseases like muscular dystrophy that you may have heard of, or Huntington's disease. But they're pretty rare, but they're exceptionally good for mouse work because they tend to be caused by, of our 20,000 genes, they tend to be caused by one gene. And with the technologies, I talked about all these puzzle pieces, the technologies are so cool today, we can take a human mutation and put it in a mouse and see what it does. And that just accelerates the path of discovery and research tremendously. I gotta tell you, someone who helps me with this slide loves to say that, who doesn't like Texas very much, loves to say that that's about the size of, if you put them all together, of Texas. I want to tell you a story, because I worked on this one, and it's a story that comes back to, I talked to you about this George Snell, the Nobel Prize winner, who the gene name does something else. That's what we're going to talk about here. So I was fortunate enough in my previous life to work on dwarfism. And that's considered a rare disease. And dwarfism, can we ameliorate the effects of dwarfism? They have a lot of life challenges for that. It's very difficult to drive a car. It's simple things we all take for granted. But so we got onto this, and I got to tell you, the study of height. Keep dwarfism in the back of your head, but just height in humans. I have one of my least favorite quotes of something that I did I must have done as a young professor. When I got into this just a few years ago in this company, this guy came to apply for a job at the company. And he gave a beautiful job talk, and he said, I studied the genetics of height. And I said, that's good, and it was a nice talk. He did a very nice, we offered him the job. He said, but you have disparaged my field, me. I asked him a question. He said, yeah, I know of you. You said bad things about my field of height. I said, did I? Did I say negative things about height? Yeah, you said finding genes for height was like stamp collecting. And I said, yeah, that probably was me. And because it's not, what you need to find genes are lots and lots of people that for whatever disease you're interested in, it's been measured in them. And no matter what disease it is, everybody measures height and weight, right? So the history of finding genes for height go like this. 2007 was the first one. 2008, up to 20. 2010, 180. 2014, 423. A couple years ago, 12,000 different genes for height, right? So I could be forgiven for calling it stamp collecting a little bit. But the problem is with that, for normal human height, is genetics is often called the needle in the haystack search. The haystack just keeps getting bigger. So if you want to make drugs, how do you know where to start? It seems like the answer would have been easier in 2007 when you only knew one. But now, you got 12,000 to choose from. There's just no way to distinguish them, to impact human height. So I was really fortunate. I was working in a company at the time who was studying this for not just height, but achondroplasia, dwarfism for that. And they had this beautiful model and this nice drug, and they put it in mouse. I had to show you some mice pictures. This is from a publication. Just look at the left over there. If you take a wild-type mouse on the left-hand side, it turns out short in length. You give it some drug, it gets a lot longer, right? You give it more of the drug, it gets longer, and so the equivalent would be humans. They put this in a clinical trial, and it worked, okay? Good story. So you got a new drug for dwarfism. And it's on the market today. It's approved in every country. It's wonderful. It's really terrific that happened. But the interesting thing here is that drug, and the genetics told us that drug isn't only relevant for achondroplasia. The genetics say that you give that drug to just normal, shorter babies, they're going to get taller. You give that drug to taller babies, they're going to get taller. It works on the general population, and the genetics told us that. So I'm getting back to this, genes do lots of things. This didn't just impact achondroplasia, dwarfism, normal human height. And so now the studies they are doing are not to make basketball players, but to those for which many of you don't have children, but when you do, they measure your children very early on, and they say you're in the bottom or the top or the middle centile of height and weight and other things. Those that are really, really low, maybe we can, and it's working. It's working. So that's a very successful rare disease story for a common condition. The condition in this case is just height. It's the haystack. And that, I think, is going to exemplify how genetics has a greater impact more than any other way. Like, if we study, and we do, type 2 diabetes, I don't keep track of how many genes are known for type 2 diabetes now, but it's over 400. It's kind of getting to the same point where we don't know where to start on that. That's really, really hard because they interact in all these different ways, and this type of type 2 diabetes is different than this type of type 2 diabetes. But what if we find a rare form, go through the drug process for the rare form, and then expand it, rare to common? I think that's where genetics will make its greatest impact in translation in the near future. And we should have known this because statins, any of the males in here that are over age 50 or something will know of statins, and some of the females. Those drugs were found in a rare disease that only impacts 1 in 250,000 people. And now it's one of the most commonly prescribed drugs out there for statins. So this is the way genetics really will have, in my view, a great impact. Different than what we thought getting into this game, but still super important for humanity. So in this case, this is a really provocative and probably wrong statement and would be challenging to many people, but if you take rare diseases and some of the cancers, we know what the defect is. We know what the mutation is. We know the gene that's causing it. And the challenge is just, can we reverse that effect? Okay? That's still really, really hard, but it's not the biggest problem to do. The biggest problem that we're getting toward today in many of these cases, especially in rare, is funding. And it's drug costs. So I got to tell you, I told you, I warned you that I like to tell stories. I'll tell you another one. This drug here is for a disease called metachromatic leukodystrophy. I got to work on it in about 10 or 15 years ago. I was at GlaxoSmithKline, and we kind of in-licensed this from an Italian investigator. And it's a really, really tragic disease because it tends to get diagnosed in families because the first child got the disease and passed away. And so then they test the family and look to see if the next child might be a carrier. And it's one of those diseases that's super sad because once the symptoms are onset, you can't turn them off. The damage is done, they're going to pass away. But if you can get to them before, this drug works. And so it was really sad doing the clinical trial because some of the kids would be enrolled in the trial, you'd find the family, but by the time you got them the drug, the symptoms hit, nothing you could do. Anyway, so I got to work on this drug, but it's a really rare disease. And there's a challenge in drug discovery that I'm sure people will have questions on, but it is the society we live in that they cost a lot of money because, especially for rare ones, because there's only 100 patients, or so, I don't know, I forgot what the number is for MLD, but it's more than that. But many of these rare diseases don't have enough patients to justify millions of dollars of investment. They just don't. So the companies aren't going to invest that money when there's no chance of return. Glaxo gave this drug back. They said, we're not going to make any money on this. You can have it. And they gave it to a company in London, and that's the last I heard of it until this came out, which was about a year ago or so? I don't know if the date's on there. 8:45, March 20th last year. And I woke up to see this, and they had carried that on for more than 10 years, got it approved by the FDA. Now those of you that are parents, think about this challenge. It's the most expensive drug in the world. So over $4.5 million. You only have to pay it once, but I don't have $4.5 million in my pocket. And how tragic it would be to be a parent with a child with this disease and to know there is a treatment. And that's a lot of social media to raise $4.5 million to do that. That's the problem that we're facing today. And that's not pointing fingers at the drug companies. That's what it costs to do that. That thing, somebody was paying to work on that for the last 10 years, even after Glaxo spent all its money to do its thing. So they're probably just trying to recoup costs. So that is not a value statement. That is a practical, this is the society we live in statement for rare diseases, which is really, really sad. But a lesson that I wanted you to hear today. A little bit about drug discovery and maybe how we can tackle this problem. So I like this, but you'll see lots of these slides if you search the literature. This is a classic view of how drug discovery works. So I'll walk you through it very quickly because it is, those of you that aren't familiar with it, it's kind of instructive on the process. So if you go to the leftmost side there, the height of all that blue sort of exemplifies the number of studies. So there's lots of basic research on every disease going on every day. Pick your disease. Alzheimer's, there's a lot going on out there, cancers or rare diseases or whatever. There's a lot of studies going on, mostly in academic settings, in universities. We get grant funding, we do some research, we move along, we find things along, we publish it, and eventually maybe we get something that we think might be relevant for a drug. And then the academic side kind of stops, because most academic institutions don't have the resources or the wherewithal or the know-how to make drugs. That's not what they do. So you just the academic side moves on and works on the next project. And eventually, on the other hand, industry finds that and picks it up and takes it forward. And where those two kind of separate has been called the valley of death, because the science kind of stops there. Academia goes back to it, and pharma's doing its thing over here, and it's a big gap. So the right-hand side of that, clinical trials and the FDA and so on, there's not a whole lot you can do there, because once you get an investigational drug, you got to test it in humans, and there's just a process that takes time to get that through. But you could do a whole lot on the left-hand side. So the view is, if we can close the valley of death and shorten or improve the success rate in basic research, we can shorten this whole project and turn that $4.5 million drug into something that's much more manageable. And that's really exciting, because we have all these tools now. So now I'm taking you into the last part of this talk that I want to talk about the future. We have all these tools. Gene editing, I don't know if many of you have heard of CRISPR, but it's a really exciting, terrific basic research tool. When I was young, I worked on a disease called Huntington's disease, a rare disease. And the way we were able to work on that disease and find the gene and look for modifiers of that gene was we found families that had the Huntington's disease, and then you look through those families and see, which child has this gene or that gene, and you map it by that. But it was completely opportunistic, because the only way you could find mutations was to find families, and if it's rare, Huntington's was a great story, because there was literally a place in Venezuela called Lake Maracaibo, where all the Venezuelan Huntington's patients, it's kind of a sad story, were just sent there. And so the families just lived there for years and years, but you could find thousands of them, because that's where they all were concentrated. With gene editing, now, if I want to create a Huntington's mutation, I can teach an undergraduate how to do that in a week. So I don't have to go observe them, I can insert them. I can insert them in anything I want, and then test it out, put it in a dish, put it in a mouse, do whatever I would like. So that's a great technology. AI I'm going to come back to in a minute, because I want to talk about it. And then the disease models, we're getting better and better. And I talked to you a little bit about the Jackson Lab and so on, and that's really exciting. Mouse models are great. There's a terrific quote out there, if you haven't heard it. It's from a statistician named George Box. All models are wrong. Some are useful. It's true. And mice are no different. They're not furry little humans. They sometimes really reflect the human biology, and the genomes are very similar to humans, but they're mice. And it's the same with other types of models as well, and we'll get to AI in a moment. But the view is, maybe we can put all these pieces of this puzzle together and shorten that valley of death and bring those drug prices down. Because otherwise, we're just trying to change society, which is a really hard thing to do. But maybe we can tackle it from our science angle and not from a capitalism or other societal angle. So the key to closing that valley of death is fail less or fail faster. And our idea is better models. We just make better models of human disease and spin that up as quickly as we can. One of my favorite types of human disease models now are called organoids, then they start with induced pluripotent stem cells. So this is science fiction, if you haven't heard of it. So you take a piece of any one of your skin, and you add some magic chemicals to that piece of skin, and it turns that skin all the way back. It reverses its lifetime to where that skin, before it turned into skin, it was a cell that could convert into anything. It could convert into a neuron, or it could convert into a heart or whatever. And so what we can do now is we can convert any one of our It has all of our DNA, it's our biology, it's converted into any cell type that we have. So that thing that's beating on the right is from a piece of skin that has been converted into heart cells. And they actually beat like that. And you can do the same with brain cells. And you can do the same with liver cells. You can do all these different ones. Now imagine the potential for medicine. The precision medicine thing I was talking about with cancer. My cancer is different from somebody else's cancer, but we can take my DNA, stick it in a dish, and turn it into that. It's perfect. It's beautiful. So that's one area that is really moving forward, where you would have animal models on one side. Animal models are really good because they're a full species. And when we're drug testing, let's say we make some investigational drug for heart failure or for stroke or something, and we can test it on this, and it might look really good, but if we put it in humans, sometimes you'll hear, oh, this drug failed because of toxic effects. It did something wrong in the liver, or it did something wrong in the brain. You can't test that here, because this is only heart cells. But you can test that in a mouse. You could test the heart efficacy here in cells. So the combination of those is the sweet spot going forward. And you'll see a lot of this. This won the Nobel Prize in this technology, won it in 2012, I think, by a guy at Kyoto University called Yamanaka. And it really is science fiction that he was able to find just a few specific chemicals you can add to a piece of skin and reduce it to its primordial state, and then do whatever you'd like to bring it into other forms. So what we think at the Jackson Lab the future really brings is you put all these pieces together. You're going to put the mouse together with the cells, and we're going to let AI do what AI does, which is find out new hypotheses that we wouldn't have thought of de novo by man, because we're kind of very linear thinkers. And maybe we put those three pieces together. I can't think of any other type of model of humans than those three on that screen. You either have animal models, or you have models in a dish, cellular models, or you have computer models. I don't think there exist any other types. So this is what we got. This is a whole toolbox for the world going forward, is to find a way to maximize how we can use those to shrink the valley of death, reduce the failure rate, reduce the cost, increase the precision medicine. Simple. And if we do that, then we bridge that discovery to the clinic continuum. So I want to end this with a conversation about AI and drug discovery, because I get asked this every day, and some of you will probably be great AI experts. I hope we could talk afterwards, because I want to learn how all this goes. But I get asked every day, are the days of mouse over? Nobody's going to study mice anymore for human disease, because the computers are going to solve this, right? It's just we're just going to come in and crack it wide open. And it may happen, right? But remember the hype cycle. These things take a long time before they deliver. And AI undoubtedly will have great successes, and already does have great successes. I mean, if you think of clinical trials, it used to take legions of these regulatory documents to get a new drug are thousands of pages. You'd have legions of people writing all these pages, and then there's all this version control and all that. AI does it now. And so it's already doing those type of things really, really good. But coming up with entirely new ways to think about biology and make drugs, we know so little about biology. The more I worked in the drug industry, the more surprised I was that any drug worked, because we just don't know as much as we really should. So this is conjecture. You can fact check it if you like, but I think it's close to correct. I know this part's correct. Billions have been invested in startups and in this field. AI is super, super hot. How many drugs we got? Not a lot. There's a recent report that says they got one. I don't know if they really did, but it's hype cycle, right? Give it time, and maybe it will. But today, when you read in fact, just last week, the FDA issued an announcement that said you don't have to use animals for drug studies anymore, because they want to encourage the use of the cell models that I showed a minute ago, which is great, and AI, which is also great, but not alone. As a drug developer, if I would ethically never put a drug in a human that I hadn't all the information I could get about whether that's going to work and whether it's going to do bad things first. And part of that is getting it out of animals. So I think these new tools will help the process, no question. They'll be terrific. But do you replace them? No, you use them all. And that's where we really need to go. So the question I leave for you is, where is AI on the hype cycle? And there are going to be parts of this that certain applications are way out the back end. Maybe it even skipped the hype cycle altogether, and I just told you the one for clinical trials, and it's great. But in terms of just completely replacing all that we know about biology and medicine, it's hard because we don't know enough to know truth. How do you train these things when you don't have data to know what's right and what's wrong? So very, very challenging in that particular application, but great in others. And I thought I'd leave you with just a couple from Jack's where it really works. So we have all these mice, right? Millions of them that we create and produce for the world. And imagine you're a little mouse in a cage, and someone takes the roof off your house, and some big claw comes in and lifts you up to test you or weigh you or administer or something. That's got to be pretty scary. So it is true that every time there is human intervention in mice, you're doing something that could be changing exactly what you're trying to measure. You know, you're getting heart palpitations or seizures or whatever because it's not normal for them to have something so invasive. So this is I think a great AI application. So what some of the teams did here in collaborations with some people outside too, is just take AI tools. AI is really good at imaging. You guys could tell me about this probably, but at putting together vast images and photograph recognition and so on. So take those tools that you could probably exist in any of our iPhone and put it in the cage so that you can monitor all these behaviors of what mice are doing at night when you're not watching and what they're eating. And they're so precise that just by the tools of imaging itself, we can accurately predict the weight by morphology of the mouse, which is pretty cool. Now, so that is an AI tool where it blew right past the hype cycle and it worked. Don't want to replace that. So I'll leave you with this little video. So this is real. This is what we can see, and already we're learning things and things like drug effects by what happens when you give a mouse a drug for seizures, say, which are very common ones to use for mice. Do they reduce? Do they continue? How frequently do they go? And you can exquisitely measure these things. And aging, sleep. One of the advantages of mice that I'm ending with here is, right now, a lot of diseases that we thought of, cancers, for example, we think of now as diseases of aging. Cancers tend to occur, more than 60% of cancers occur in people over the age of 60. But yet we study them in newborn mice. That doesn't make a lot of sense because the mice haven't had a chance to age up to that. The beauty of it is, though, a 2-year-old mouse has the same age as a 70-year-old human. So with that and with these type of tools, what we're doing now with a lot of drug companies and with others is we're just growing mice to let them get older so that they become the right tool for the job. And that's what's coming. So for the aging phenotypes and the aging diseases, a lot of the immunological disorders are aging. The Huntington's disease that I talked about before doesn't have an onset until age 55 or so. So it doesn't really help to study it very early. So that's where this field is. And so to summarize, the fulfilling the promise or chasing the hype, I think it's both. In cancer and rare diseases, this field has knocked it out of the park. And I personally feel really fortunate to have been alive at a time to watch a field go from the basement Marriott to Maroon 5 and Macklemore. And we could talk about Macklemore. Macklemore, if any of you know Macklemore, has colorful language and came to this conference with a bunch of old-timers like me dropping F-bombs right and left. That didn't go over all that well. But that's the way the field has gone, and it's a privilege to have been there. How long to get there with AI? Will it replace it? I don't know. It's an indispensable tool in the toolbox, but not the only one that we have. Unprecedented time, and what can we do scientifically to address the problems that are more societal? Thank you very much for the opportunity. I'm happy to take questions, yes, if anyone has any.
Any questions? Oh,
Got one
okay.
here.
I gotta hoof it over here.
Thank you. I appreciate your talk. Just if you could comment really quickly where you see like silencing mRNA drugs coming in, because right now there are a few of them on the market, but obviously being able to essentially turn off a gene with a silencing mRNA drug is potentially a huge tool going forward.
Yeah, I think we could put silencing mRNA, or we could put any of the RNA or DNA-based therapies in the same categories. I think as delivery modalities, I think they're terrific, right? And I think the RNA therapies hey, there's a great example. Take a little specific ASOs or any of the RNA-based hype cycle, 20 years. You know, they took a long time, and now we have approved drugs for some of these. I think there's a number of new modalities. I mean, 20 years ago, we basically had small molecules, chemicals, and the drug companies would go out there and they'd build these vast libraries of different chemical structures, and they'd screen whatever they were interested in across all those. Now we still have those. We have different types. We have monoclonal antibodies. We have gene-based and RNA-based therapies. We have gene therapies, which is what that metachromatic leukodystrophy example was I gave. It's a one and done, which are great because you get, I mean, price is not so great, but the one treatment, and they can be effective potentially for a lifetime. So all of these, I think, are the future of what we've got. The hard part is knowing where to target, which is the right. You take these complicated diseases like type 2 diabetes, we haven't broken it down yet. So what we know probably for sure is there isn't going to be a one-size-fits-all. And so how do you study those? And it's that biological side, I think, that will allow us to best use the modality side that you're describing.
Any questions? So what do you think is, I'd say, the most exciting advance in genomics from your perspective? Going forward, what do you see is going to be the next major exciting cycle?
You know what? That's a really, really good question. I could talk. There's this wonderful circular trend that exists in genomics, and it probably exists in all walks of life and all sciences. But I've got to see it in genomics. So you have new discoveries will drive advances in new technologies. Take DNA sequencing. You start a little bit, and then the sequencing gets better. And the better the sequencing gets, the more discoveries you get. And you get this sort of cycle that keeps going. So there are technology advances that I think things like the discovery and advance of CRISPR for gene editing change the field, completely transform the field. I think the genomics now that we knew but didn't really exploit is we think about, a lot of people used to say, it is true, you're born with the genes, they don't change, right? You get what you get. And we think of that as a static system, and that's just but actually the genes are modifying each other all the time. I drink this water, it's going to change a little thing. They're not going to change their map. They're the same genes, but they turn each other on and off. So they're doing different things all the time. And I think that epigenetic type of profiling and that work will help a lot. And we don't know it very well, but it's happening all the time. And it kind of explains why the genetics, just knowing the map of your genes or my genes, doesn't tell the whole story. It's that interplay of everything else that we've exposed ourselves to over our life and currently.
Yes.
All right, thank you for your talk. My question is, how do you think the withdrawal of federal funding for research is going to affect drug development?
You really want to ask me that question? Aren't we live here? Aren't we taping this? This is the topic every day for all of us, and we're living it. My biggest frustration of the things that are going on right now is I fear that we'll lose a generation of scientists. And we're seeing it already. And it's your generation, not mine. And it's really, really tough where people, this has been for years the place to come. And people came from all over the world because this is where you did it. This is where the drugs come out. And yeah, it's got lots of flaws. Of course, every system does. They're not doing that already. And they're not even, people aren't even staying. So I will dodge the question specifically of what that has on drug development or research, but you just ask yourself, you take away the scientists, where's the science? And that's what's beginning to happen. And I just think that's a horrible tragedy, personally.
Thank you again for your talk and taking time out of, we could all imagine, is a very busy schedule running the Jackson Laboratory. Kind of piggybacking off of that question, what would you tell to the students here at Husson University who may feel that their futures in science are no longer available? What words of encouragement or motivation can you give our students?
I think that's a question we get asked a lot, too. What do we tell the scientists? I can only draw on my own experiences on that. I was lucky enough to find my North Star, something that I loved, early. And I followed it. And I made decisions, some right, some wrong. Some went forward, some went back a little bit. I wouldn't change a thing. And I think if I would like to think that's still the case, right? Will the challenges exist? For sure. Will they be different? For sure. But, I've been fortunate enough, I've been in this field, since late 1980s, I don't feel like I've ever had a job. I just did what I wanted to do the whole time. Now, there'll be near-term and maybe longer-term impediments to that, but if you find what you love, you got to go for it.
Yes, another question. Where did I?
Again, thank you, but I also, Miss Potency, Jen, she asked about funding, but do you think that AI plays a role in the fact of losing a generation of researchers and scientists? Because I think the mentality around it has changed since AI has kind of become the hype. So yeah, do you think that might be playing a role in that as well?
It's a interesting point. I hadn't thought of AI as a risk factor for this, right? But it could be. I think, and I hope I gave the right balance. I think I'm excited about AI. I think it's going to do wonderful things. I just don't think it will do the transformative things in all areas at the same pace, right? That'll be harder. But that is the problem. Is that the perception is it's going to solve everything. And there is, the FDA announcement I just said from last week speaks to exactly your question. So probably it's a predictor to some extent, but I also think there is truth in that it will help solve the problem. But as long as we have the limited understanding that we do, we need to be able to validate things. I love the idea of having AI come up with completely wacky new hypotheses about human biology. We need exactly that. But then we got to test it somewhere. So that's what I fear, that if we take away so much of that research infrastructure that we can't find truth in science, then we'll be chasing AI in really dangerous and scary ways that sometimes will be right and sometimes won't.
Oh, back here.
Thank you. Have you found at all if the research you're doing on genomes and AI make it easier to find solutions for difficult conditions such as ALS and Rett syndrome?
Yeah. I'm with you in hoping that we can with ALS and Rett syndrome. Those are two of the real, well, they're all terrible diseases, but those are some of the more common rare diseases. I don't think those big impacts have been seen from AI yet in those, but it's early days on this. We are in a positive sense for both of those diseases that you raised, because there's a lot of studies going on. So there is a lot of data being generated, and what is AI like most of all? Data. So those are probably in better case than my metachromatic leukodystrophy, where very few people are studying it because it's so rare. So fingers crossed.
Is there another question?
Here's one.
Thank you so much for your nice talk. I really enjoy it. So I'm in chemistry. I want to ask a question related to cancer treatment. So a lot of times cancer patients undergo like chemotherapy and a lot of other treatments. And then a lot of times then they will look fine, but sometimes they just look fine, but it may not be as good as we see because there may be some minimum residual disease. So the leftover minimum amount of cancer cells are very dangerous because they're in the level that cannot be detected by FDA-approved detection. So they can proliferate to disease burden, and then we have cancer relapse. So my question is, in your opinion, what are the important tools or directions or strategies we can use in minimum residual disease detection in cancer patients?
Yeah, that's a really specific question, and I'm not an oncologist, so I don't want to give a specific answer to it. I'll give a generic one that I think would apply to cancer, but would apply to other diseases too. And I've said this in public, and I've been challenged on it. I might be wrong in the fullness of time, I might not. We have some pretty exquisite tools biologically now, right? And cancer is included, right? We have CRISPR, we have all these things that we can intervene on. We have your chemistry, we have amazing small molecules, we have the RNA therapies, we have all these. The biology side is we're getting a sharper and sharper scalpel. And then we link it up with something that's really dull on the other side, which might just be tumor size, shrinkage or something. I think we need to refine the left-hand side of the equation as much as the right-hand side. So maybe the trick to your cancer question is better refinement of what we measure rather than how we intervene on the chemistry, but what we really measure to see what's happening. And maybe the tools we need to develop are more and more exquisite measures of how much cancer cells are left, whether they're circulating or otherwise. And maybe we do that as much as trying to find new drugs. Because maybe the drugs are there, we just don't know which people they're in or how to administer them most effectively.
Any other questions?
There's one over on the far side over there.
Coming through.
Hello. For our students that may have been inspired or their minds are intrigued about this type of work, and in terms of the Jackson Lab context, what do you look for in one of the 3,000 plus employees that work at Jackson Lab?
Oh, you're going to let me give a shameless plug for curiosity. We look, whenever in any walk of life, whether it's a Jackson Lab or someone else, you can't expect people just entering on the research side of things or the full article, right? We all started somewhere. You don't have all the tools yet. You don't. But I think some indispensable ones are curiosity. I think a willingness to try something and recognize that it may be wrong and just bounce back. I think we talked this morning about adaptability. So they're just human nature concepts more than coming in and saying, I need to have this technique locked down or that technique. I don't think so. Science I find it a terrifically rewarding field, but it's a really challenging one because it's built on failure. For every you saw the funnel there. There's an old, often quoted, for drugs, 95% fail. It's way worse than that. Because that's after you've already got a drug that you're testing. It's like 99 with 10 digits % fail on that, and you're building a career on that. So you've got to have that mentality that says, that's okay, I'm learning. Maybe it's 2 steps back, 1 step forward, maybe the other way around, but I'm getting there. And I think those type of people, they find a home in science and they thrive. And hopefully, wherever the question was, for that next generation, we'll find a path for them to make it through. And I hope you do.
Yes.
How would this fit with students? What would you look for students that want to work at the JAX Lab, an internship or a clerkship or something like that?
What would I look for?
What would you look for in a student?
Oh, in students so, if you talk to different colleagues at the Jackson Lab, you'll get different answers because people have different specialties. Some might want more experience in molecular biology or chemistry or whatever. In my own field, because I come out of statistical genetics, so it's all quantitative things, I would look for students with flexibility. Students that have, I like breadth over depth almost, and you kind of need it in this field today because it is so complicated. So the ability to move from and accept one type of data from another. I used to tell students that I think the greatest attribute you can develop as a student, more than in any discipline, is critical thinking. The ability to pick up a paper, go to a colleague, go to your posters down there in an area you know nothing about, and ask questions about it. I think that, to me, that person just went to the top of the list. That they could come to. They don't have to be good questions, and they often aren't. That's okay. But critical. That's what I learned along my career. People just threw me in it and said, you got to sit on this review panel. Well, you kind of figure it out, and you learn on your way. But that is a skill that just takes you through life. Critical thinking, not overconfidence, not boastful, just inquisitive inquiry.
One more question. Yeah, one more question.
So this is a more personal question to you, but what's your preference on being in academia or in industry?
Gosh, I haven't been asked that one for a while. I used to get asked it all the time. It kind of depends on the state. They're two different. They're different, and I don't want to give a biased answer to steer you in one direction or another because both have great attributes. In industry, the resources are greater, especially now as we talk about funding challenges. Now they may shrink there too. That'll probably be a knock-on effect. But today, they're greater, so it means you can pursue new ideas quicker. In academia, you have a new idea, you write a grant, a year, 2 years, 18 months later, you get to work on that. That's not the case in industry. The downside of that is industry in this country, globally really, in pharma industry, is driven in a capitalistic way, which means for good reasons, if there is not seen to have a return on investment to study this problem, you can wake up in the morning and something you've been working on for 3 years is done. And you have no say in that. And that's okay, because you can work on other things. It doesn't mean your job is done, but it means that project you just thought long and hard about for 3 years is over. You sign up for that. And some people can't take it and some can, but you just have to accept it. In academia, you could keep pushing that. Right? You could squeeze every little bit out of it. As long as you can get the money, and sometimes that works. That's just what it needed, is you were just looking at the problem the wrong way for 3 years, and you finally looked at it another way, and it worked. So I think you are in a generation that has it far better than I did, where you could do both. And and that is, you could stay in academia and expose yourself to industry via collaborations. Even sometimes by part-time work and so on, and get a chance to test drive before you go. I didn't get a chance to do that. It was either you're all in or you're all out on either one. And so that's what, I've got a son, my son is just finishing his MBA, but he's making that decision right now, which direction to go. And I'm not pushing him either way, except to say, see what fits for you. Get as much data as you possibly can, and then take that path.
Okay, well, thank you very much. Really appreciated that great talk. And how about another round of applause to thank Dr. Wall. So that concludes our 15th annual celebration of research at Husson University. Thank you for participating this afternoon, and look forward to seeing you next year or whenever. So thank you.